In our previous class, we have discussed the interference phenomena by the division of wavefront method, and also discussed the pioneer work of Young's, that is the Young's double slit experiment, and the shape of the fringes and the the fringe width. And now we are going to discuss the other experiments regarding the formation of interference fringes by the division of wavefront method, and the very important one is Fresnel's Bi-Prism. In this Fresnel Bi-Prism, one has to first understand what is Bi-Prism. Here in this picture you can see the Bi-Prism, where the prism angle is alpha, which is very small, nearly half degree, that is 30 minutes. It is made by the technique of it is called the grinding technique, rubbing a flat glass surface. The prism has been made, so you can think how sophisticated the technique is, that half degree of the angle of prism is made by this technique, so it has to be a very sophisticated technique. And now what happens when a source of light is placed in the back of the Bi-Prism at a distance small a, the source emits light and it will travel in the forward direction, and you may get the interference fringes in the screen placed at a distance d from the source. How the interference fringes are occurred here? See, the rays coming out of S, you can think of that. The rays, see this ray, this is the number 1 ray, and this is the number 2. So number 1 ray goes into this direction, and by the mechanism of prism it will be deviated towards its what we call the thick end of the prism. Here the prism, you can think also that Bi-Prism is made up of two back-to-back prism connected to each other. So one prism is this one, this triangular, and this the another prism. So light is incident on the lower part of the prism and will be deviated into upward direction because the thick part is in the upward direction. So the light choose this path. Similarly, the number 2 rays deviated in this direction, and if you extrapolated the rays into the backward direction, that it will be thought of that they are coming from two different sources, S1 and S2. As we are seeing from here, we can see S1 and S2 as different sources, but these two different sources are nothing but the virtual images of S. So S1 and S2 has to be coherent in nature. So coherent sources are achieved, so interference fringes will be appeared in the screen placed in front of the Bi-Prism. Now let us calculate the fringe width or the other things by this experiment. So if n is the refractive index of the material of the Bi-Prism and alpha is the base angle, that is angle of prism, then n minus 1 into alpha will be the angle of deviation. That is, what is the angle of deviation here? See, for number 1 ray, the ray is going in this direction, but the rays gets deflected into this direction, so the angle of deviation is this angle. So by the method of so the opposite angle will be this equal, and this will be again the angle of deviation. So if you call this angle deviation say delta, then the same angle of deviation will be this here. So delta will be the angle of deviation. So this delta, this is another delta. So 2 delta is the angle between two rays which are shown here. So D can be formulated as D is equal to A into twice delta. So D, that is the distance between two coherent sources, can be evaluated by this formula, twice delta into A. We are using here the S is equal to R theta formula. So what is delta? The formula of delta is n minus 1 into alpha, which is in your class, in your 11-12 class. So this is the angle of deviation. So the distance between S1 and S2, what I have told, that D is equal to twice, D means S1 S2 distance is equal to twice of A into this angle. So twice A, actually A into twice of this angle. So twice A, n minus 1 into alpha. Now let us take a typical example. N is equal to 1.5 and alpha is equal to 20 minutes near about. So in radian, this is the radian, and A is equal to nearly 2 centimeter, which will get the D is equal to 0.012 centimeter. But there is an experimental challenge, because alpha, measurement of alpha is very tricky, and there is a chance to mount some error while measuring the angle alpha. So we has to move into a more precise experiment, so that this small d, that is the slit separation S1 S2, can be measured in a good accuracy. So for this, let us use a technique where forget about interference, just look at these two sources S1 S2 and distance between them as d. And if a convex lens is placed between the slit and the screen, then in two distinct positions the images will be very much clearer to our eyes or to our telescopes. So this is a theory also you have learned in your previous classes in your schools. So L1 and L2 are the two positions of the lens from where the two distinct real image is formed of the slits. So L1 will be when the lens is at the position L1, the image length is B1 and the object length is very simple, D minus B1. So using this technique we can find the height of the object, that is D here, the slit separation, and the image height in both cases L1 and L2 can be measured by telescope. Say these two image heights are D1 and D2. So the object height will be D is equal to root under of D1 D2. The proof is not given here. You can consult your textbooks at your 11 or 12 class levels. So this technique is very much accurate to determine the slit separation D, and capital D is very much easy. It is B1 plus B2. So give a typical example. You can find the beta, because beta, the fringe width, consisted of both small d and capital D. So you have to measure this very accurately, and beta can also be measured by this method. So lambda, if lambda is unknown to you, see here it is written, once beta is known, lambda can be determined. This is the simple formula of fringe width which we have deduced in our previous class for Young's experiment. So beta is equal to lambda d by d, so lambda is equal to small d beta by capital D. So beta is known by this experiment. One can find beta very accurately, and small d and capital D. So lambda can be get, because the wavelength is a thing which cannot be measured by a meter. Okay, there is no meter, there is no instrument which can directly measure you the wavelength, that is the wavelength of this light is this. There is no meter or like multimeter thing. So these are the meters, that is the Fresnel Bi-Prism or Young's experiment. Those experiments can be used to measure the wavelength very accurately. So this is the application of Fresnel Bi-Prism experiment. And now very interesting thing, what will you see when white light is used in case of interference experiment? Let us take the example of Fresnel Bi-Prism. It is I am describing with Fresnel Bi-Prism, but it can be understood that the Young's experiment can also explain this phenomena of white light interference in similar way. So don't get confused with that. So let us take a point. Now first thing, the wavelength of visible light. We know violet has the minimum wavelength 4 into 10 to the minus 5 centimeter, and red has 7 into 10 to the minus 5 centimeter, that is 7000 angstrom of in the range of 7000 angstrom of wavelength. So if you choose a point, now what is the central fringe? We have discussed that central fringe is always maximum, so white light will be white at the central fringe. So central fringe will be bright, and it will be white colored, because all colors in a white light will satisfy a maxima condition, that is the constructive interference condition at the center of the screen, because the path difference between for each of the colors will be 0, and 0 path difference means the even multiple of lambda by 2 means the maxima condition. So the central fringe will be bright and white here, as you have used the white light as your interfering light. Now let us take a point P such that at the point P, see, we are taking 3 points. O is the central point which is white, and here these are not any more monochromatic light, it is emitting white light, like your helium light, your mercury lamp, etc. Let us consider 3 different points, P, Q and R. P is nearer to O, Q is nearer to P, and R is relatively far away from the central region. So these 3 points we will consider here, and let the P point is such that the path difference between 2 rays is 2 into 10 to the minus 5 centimeter. So 2 into 10 to the minus 5 centimeter is equal to, you can think that the half of the wavelength of violet, so lambda by 2. Lambda by 2 means, what does it mean? Lambda by 2 means the destructive interference condition for the violet light, because n plus half into lambda is the condition for destructive interference, that is dark will be appear for the path difference is equal to n plus half into lambda. So it has been studied in our previous class. So violet wavelength satisfies that condition of first minima at this point P. So violet color will be absent, but in case of other colors which are of greater wavelength than violet, will satisfy some partial destructive interference, that is partial constructive interference also. So violet color will be absent, and consequently if you omit the violet color from a white light, then the rest of the light will be reddish. So reddish color will appear at the point P, and the point Q, which is apart from P, if it has a value 3.5 into 10 to the minus 5 centimeter, that is at point Q, the lights coming from the slits S1 and S2 has path difference in the order of 3.5 into 10 to the minus 5 centimeter. Then surprisingly it will satisfy the condition of lambda for red by 2, that is the red light will satisfy the first minima at this point Q. so red color will be absent there. The minima of red color, that means the red color will be absent, but it satisfies almost the, see, the violet wavelength is 4 into 10 to the power minus 5, so 3.5 is very nearer to that. So for the violet color, this point satisfies the first maxima for the violet color. So the color will be violetish, rather bluish there. So but if we choose a far apart point, say R, where the path differences between the rays are 30 into 10 to the minus 5. Okay, so we can back calculate it. So what colors will satisfy the maxima or the constructive interference there, and what colors will satisfy the minima condition there. So first take the maxima condition, where 3 into 10 to the minus 5 centimeter is the path difference. So if we divide by n, then we will get the wavelength of the light corresponding to the constructive interference. So n, if we put n is equal to 1 there, then it will give you nothing, sorry, 30 means no visible light is there. If you put 2, then 15, if you put 3, if you put 4, nearly 4, then it will give you 7.5 into 10 to the power minus 10 centimeter. So n is equal to 4, that is the fourth maxima will be for the red light, because the wavelength is 7.5 into 10 to the power minus 5 centimeter, which is of red. And if we put n is equal to 5, then you will get 6 into 10 to the power minus 5 centimeter, which is yellow. So similarly, red, yellow, greenish yellow, violet will satisfy the maxima condition at the point R of different order of fringes. For red it is 4th maxima, for yellow it is 5th maxima, for greenish yellow it is 6th maxima, and for violet it is 7th maxima, and so on. So those colors will be present there, and what colors will be absent? So you have to divide this path difference by n plus half. So put n is equal to what do you put? Say n is equal to put 4. So 4.5, 30 by 4.5 will give you 6.67. So fourth order dark fringe of orange will be, because this wavelength falls into the orange category, so orange will satisfy a minimum there at the same point R, and yellow will construct a destructive interference of different order at that point, or indigo. So some colors will form, these colors will be absent, but see what colors are present there as a maximum. Red, violet, that's enough, and yellow, the average light, and greenish, also an average light. So average lights and extreme 2 lights are present here at the point R. So the R point will be white. As viewing by a naked eye, we will see a white light at the point R, and after that point R, we will see the same picture, that is white light will be appeared again. So what we see in a summary, when we use white light as an interfering light in case of interference experiment, so the point O, the central fringe, will be appear white unanimously, and then P will be some reddish color, and then Q will be in blue, that is the colored fringes will be there, and after the point R, or in the vicinity of R, from the vicinity of R, the fringes will disappear and the white light predominates. So if you locate in some experiment where your central fringe is, you should use white color, because if you use the monochromatic light, say sodium vapor lamp, sodium light, so monochromatic light will give you so many interference fringes, so that we can't detect practically where the central fringe is in our eyes. But using white light, the central fringe should be white, other fringe will be colored. So in naked eye you can tell that here is your central fringe, which is bright, which is white. Okay, so white color fringes are of use when you are targeting to measure the central bright fringe. Okay, and for the monochromatic lights, the central bright fringes will definitely appear, but it is confusing to detect it by our experimental setups. Now next topic is the displacement of fringes. What the phenomena is, let us take this picture where S1, S2 are the two coherent light sources and giving us interference, and the slit separation is D. But when say thin sheet of glass, that is transparent media of thickness T, it is shown here, very thin transparent sheet is placed in front of any source S1 and S2. Here is in front of S1 it is placed, so it will shift the fringe pattern by a linear distance. Okay, we are to calculate the slits, we are here to calculate how much the fringe pattern shifts. So in doing so, first we have to understand why the fringe patterns get shifted. Let us now consider a case when, say, the light is coming from S1 and reaches the point P. How much time it will take? If the sheet of, that is the glass plate, is not there, then the straight line S1P distance by velocity of light c will give you the time. But here the light travels in air by a distance S1P minus t. Okay, so S1P minus t distance will be traveled into air, so the time is S1P minus t by c in air. But what is about the distance traveled within your material? So it is t thickness it is traveling, so t thickness by the velocity of light in that medium, that is not c, that is v. So thickness t by velocity v will be the time taken to travel this direction. So the total time will be S1P minus t by c plus t by v. This is the time taken actually by a ray coming from S1 and to reach the point P. For S2P it is simple, S2P by c, because it is totally traveled into the free space. So the total time what I have described, it is written here. And v, what is v? You can use the formula of refractive index mu of the glass plate is equal to the speed of the light in vacuum c by v, the speed of the light into that medium. So v is equal to c by mu, and let us put into that equation, we will give you this part, so c will be common, and S1P plus mu minus 1 into t by c. So the reason behind the formula to be written like this is, see, if the thickness t is not present there, then the path will be S1P by c, sorry, the time will be S1P by c. But now see, the path taken by the light is increased by an amount of mu minus 1 into t. So the path difference should also increase by amount of this mu minus 1 by t, mu minus 1 into t. So this is the extra path difference generated into this experiment rather than the previous two experiments what I have described to you in case of Fresnel Bi-Prism and Young's experiment. So mu minus 1 into t is our of special importance. So the net path difference is this. Again, the net path difference formula we have that S2P minus S1P is equal to dy by capital D. You can see this formula while I was describing the fringe width calculation. There is a step where S2P minus S1P is equal to yd by d, where y is the distance of the point of investigation from the center of the screen. So this is the path difference, but here there is another path difference which is your mu minus 1 into t will be there. So the effective path difference at p is this, okay, because here, let us describe from the beginning. At the point P, the effective path difference is given by S2P. S2P is pure path because it is traveled into the free space, but S1P is increased. S1P is increased by amount of mu minus 1 into t. So the net path difference is this, S2P minus S1P plus mu minus 1 into t. So you can write S2P minus S1P minus mu minus 1 into t. In place of S2P minus S1P, let us put yd by capital D here. So the total path difference is this. If at point P the constructive interference happens, so this path difference will be lambda d, n lambda. Then you put this, and where y can be reduced, y is equal to d by d, and this formula. So in the absence of path small t is equal to 0, you will get the previous formula. Now the central bright fringe. Central bright fringe, you can take n is equal to 0. You can think that in the previous experiments, central bright fringe is at a distance 0 from the center, okay. But now see, if you put n is equal to 0, it will give you capital D by small d into mu minus 1 into t. So central bright fringe gets shifted by amount of this, okay. If you calculate by not taking central bright fringe, by taking nth bright fringe, the results will be same because the fringes are equispaced. So in lambda term will be vanished and the results will be same, d by d into mu minus 1 into t. So the fringes are shifted by amount of this, okay. This shift, if we measure the amount of shift of the fringes due to this thin sheet of glass plate, it can be measured. And for this, what we have discussed in our previous topic, that the interference of white light, if you use the white light, then the central fringe will surely appear bright and white, and if you place a glass slab here of thickness t, then you can see by your naked eye that the white fringe shifted at the point O prime. And if we place this glass slab into the lower part, then O prime, that is the central fringe, will shift towards down. So by this shift can be practically measured, and if you measure this shift y0, and d are known to us, mu is known to us, so small t will be deduced from here. So thickness of very thin glass plate cannot be measured by your slide calipers or screw gauge. It is a very unique technique to measure such glass sheets which have very small, it is smaller than yours your what do we say, um, what do we see, your slide calipers, or sorry, that is in your biology experiments you have used, what you have used, that where your blood has been stored, those glass sheets are very much thin, but the glass sheets thinner than those can be measured by this experiment. So, but one thing you should remember, the fringe width is constant. You can prove it from here. So it is very evitable because the fringes are equispaced to each other, so the fringe width should have the same value, and fringe width will not increase or decrease in this case, but the whole fringe system is displaced by amount of this value. Okay. Now our last topic of another device. Let us take study another device of making interference patterns by division of wavefront. Here S1 source is used and it is placed in front of a mirror. It is called Lloyd's mirror experiment, and here S1 slit is placed at very what you call in the horizon direction, very nearer to the horizontal direction of the plane mirror. Okay, then you will see some interference fringes. What is the reason? Reason is that, let us follow two rays. One is this, two extreme rays are drawn here. One here, number one ray gets reflected and goes to this direction. If you back, it will appear that it comes from the point S2. Similarly, this point will converge to S2. So S2 is the virtual image of the actual source S1. Now S1 and S2 will be in the surely will be the coherent sources, because S1 give birth of the point S2. Okay, so phase relationship will be very much constant with time, and so they will be treated as coherent sources. And see what is the overlapping region. The lights will be emitted in all directions, but in this direction, this cone like direction S2BC, in this direction, this is the overlapping region where the two rays coming from one S1 and other S2 will overlap to each other to give the interference pattern. So BC will be the localized place where you can see the interference fringes. There is a very interesting thing in this experiment. Why this experiment is very much remarkable to study, the phase difference between the rays. See what we have studied earlier, that the interference fringes will be constructive in nature when the path difference is in lambda, that is the even multiple of lambda by 2, and when it is odd multiple of lambda by 2, that is n plus half into lambda, then the destructive interference happens. But here the phenomena is just opposite. Why? I am telling you. Because of the reflection from the denser surface. See, this is air, but this is glass plate. So this thick glass plate, and glass plate has the refractive index higher than the air. Okay, so the reflection will produce a mandatory pi phase difference of the reflected ray. It is called Stokes theorem, which I will discuss in my later class, in our next class, very elaborately. But I am touching the main point of Stokes' law, that when a light gets reflected from a surface which is backed by a denser medium, that is denser medium resides on the bottom of that surface, then the pi phase difference appears to the reflected light than the incident light. Okay, so there is a pi phase difference extra. So pi phase difference extra means your path difference is lambda by 2 amount extra, because we have the relation 2 pi by lambda into path difference is the phase difference. So phase difference 2 pi means path difference is lambda by 2. So lambda by 2 will be added here. So consequently, when your condition of constructive interference was in lambda, here n lambda will satisfy the minima or destructive interference. On the other hand, if the path difference satisfies the n plus half into lambda, that is the odd multiple of lambda by 2, then it will satisfy the constructive interference, that is the maximum, because of the extra path difference lambda by 2. Okay, so this is the very remarkable experiment done by Lloyd, and in conclusion I would say that what we have studied at this point of time, that we have studied what is the coherent light sources, what does it mean, and what happened to the interference pattern when the light sources are not coherent. It is incoherent light. If you use, then no interference pattern will be observed. We will observe a general illumination, that is no variation of intensity will appear on the screen. If you want to vary your intensity on the screen, that's brighter pattern you want to get, then you should choose the perfect coherent light sources. And by choosing this, the techniques are different for different methodologies, for different experiments. Like Young's experiment, there are two pinholes or two slits are used and one source, the back of them, to make the two sources coherent in nature. In case of Bi-Prism, the different techniques has been used, and in case of Lloyd mirror. And also we have seen what is the shape of the interference fringes. It is non-localized. We have seen in case of Young's and Fresnel Bi-Prism cases, wherever you want to place your screen, you will get the fringes, but as you place the screen, so the fringes will appear in 2D, and for this the hyperbolic image will be appeared in straight line or in hyperbolic nature or in circular nature, so depending upon where you place your screen. Next, the fringe width is calculated, and after that a thin sheet of glass plate, if we place it in front of the screen and in between the screen and the slits, and rather the screen and the coherent sources, then it will shift the whole fringe pattern by a by a constant amount. So, and also what is the use of white light interference in the experiments. And in the last case we have studied the Lloyd mirror, where the fringes not appears everywhere. It has some localized points and localized direction. It is called localized fringes. And there is a Stokes law, what we will discuss in our next class elaborately, appears, and for this the interference patterns changes. The condition of interference patterns, that is a constructive and destructive interference patterns, just gets reversed what we have discussed in our earlier cases. So thank you.